Hello, hello! So today we'll be doing topics of recursion and interfaces. So these are some of the more advanced topics that are probably beyond assignment 2, but it's okay, we'll have our assignment review session as well. But today we're doing recursion and, of course, interfaces. So what is recursion and what are interfaces? Well, today's goals will be to cover that and to explain it. And let me just update my current thing here. Alright, so today's goals will be to talk about what is recursion, what is an interface, and how we can work with them, assess their time complexity, and all this stuff. But before I get into it, are there any questions just off the bat coming out of reading week? Anybody wondering anything that I could take care of right now? Alright, and assignment questions are welcome as well. Just whatever you may be wondering, I can answer, and otherwise I can get right into it, and we can start on recursion and interfaces. Alright, ooh, got one in the chat here. Are you getting any error messages in the A2 mini tester, or are any of you? Yeah, okay, well, all of y'all are welcome to discuss all of those, and be aware that making your own testers is also a good idea, and you can address any errors you might have in the debugger. But now getting into recursion. Here we're gonna by the end of today we're gonna understand what that tree over there is. We're gonna understand what a recursive algorithm is, why we want to use it, why we care, and as well as what an interface is and everything. So let's get right into it and talk about the concept. Does anybody here know what it means for a method to be recursive? What is recursion? What do I mean when I say recursion? To go into itself. So, yeah, what would that mean? When a method goes into itself, what is that, and does anybody know why that could ever be useful? Well, maybe it can be useful when we have to do some sort of repetitive task. So first I'll get into sort of the what of a recursion and a little bit of the theory behind it. And then afterwards we can go into some implementations and we can use it to our advantage. And at the end I'll show you a very cool recursive algorithm that we'll work on next time, which will allow us to create like a player for any game that's quite optimal. So first, we want to talk about what is a recursion. Well, it's calling a method from itself. So here we can see in this little method I wrote on the side, it's called foo. This method is recursive. You can see the little icon there, like the arrow around the green dot. That means that is a recursive call. So could anybody tell me, what does this foo method do, just off the top of your head? And you're welcome on the mic as well.
It takes an integer, prints there's that whatever integer number of bugs in my assignment, and then prints again, but lowers the integer number until it reaches 0.
Yeah, that's right. So when you put an integer into this, let's say integer 5, it's going to say 5 bugs in my assignment, 4 bugs in my assignment, 3 bugs in my assignment, 2, 1, and then it's going to stop. So why does this method stop? Why does this method stop when you reach 0?
Because you're returning the input without the recursion.
That's right. So we're able to recurse, and recursing means that every time we do it, we run this method on input which is smaller by 1. So gradually, we kind of reduce our input down to where it needs to be, which is called the base case. So every recursive algorithm follows this pattern. This is what I tried to come up with as my simplest possible recursive algorithm. Maybe there's a simpler one out there, but this is the most basic one I could come up with. Where it, first of all, checks if you're in the base case, then it does some sort of action, and then it recurses. So here what we can see is the base case is in blue. The base case is the non-recursive step. It's what happens when we don't call ourselves. Why do we need this? Well, this is how we're going to escape from our recursion. If we just always do recursion, we're going to be in an infinite loop, right? You see how that would be? Like we just go recurse, 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 recurse. We don't like that. So we need this blue base case so that we can stop our recursion. Then the second part of it here, which is the system out print line input bugs in my assignment, that one is the regular case. That one is like, or the recursive case, where we actually do some sort of action. So this print line could be any sort of action. It's just, you can do whatever you want here, as long as it does something with our input and or improves our input. And then we have, with this little green dot in the circle, which you'll see in your IDE as well, the recursive step, which is that it will modify our input so that it progresses through our data structure, and it will continue doing this loop over and over again. Or is there any questions or confusion about these first two things that we've talked about in recursion or this method I've written here? Any questions about it? Anything you're wondering? All right, so I'm assuming it's pretty clear now. So can somebody tell me what happens to the call stack when you run this method? So when I call the method foo from my main method, what happens to the call stack? So the call stack is where methods go when you call them. So you call a method, it gets pushed onto the call stack. Then when you return, it gets popped from the call stack. So could somebody tell me what happens in the call stack when this method runs, when you call this method?
Push the first one and keep popping and pushing the next one.
Yeah, actually, well, you're right. It does keep popping and pushing. But what it will do, imagine that every time you call the method, so like here, foo input -1, every time you call that method call, what it does is it pushes that onto the stack. And it says, we're going to call foo with an input of, let's say, 5. Then, inside of foo, it calls foo again. So then the call stack pushes again, and it says in foo on 4, foo on 3, foo on 2, foo on 1. So if anything, if you imagine it, the call stack would look like, do I have any stack of anything here? Not really, but maybe I'll use USB drives here for this. So these USB drives could represent our method calls, right? So first we call foo, then we call foo on a number that's one smaller, and one smaller, and one smaller. But what happens when we return from this stack? Like, imagine this is a stack of methods, foo on 4, 3, 2, 1.
Your screen? I think at least what I see is the recursion and the black screen.
Yeah, sorry, 1 second. You should be seeing the screen with the slide and then with a small face cam of me in the corner at the moment.
Yeah.
So you see, imagine this is our, here, like this stack of USB drives in the webcam. Imagine that this is our call stack. So each of these is a call for a foo, 4, 3, 2, 1. So what's going to happen when I hit the return statement of the top foo statement? Like the top foo method, I hit return. So what's going to happen to our stack?
Does it pop the whole stack?
Yeah. So imagine we return from this method foo, which is foo of 1. It goes away, right? We're done, we returned it. So now in here, we're back here, but where do we land? We land right here on the return statement of the one above. So we land on the return statement of foo 2. And then right away we return, right? Because we already have this evaluates and we return. And we pop from the stack and we pop and we pop. So that's actually the core difference between recursion and a normal method call. On a normal method call, we push one thing from the stack, we finish it, we pop it from the stack, right? You see how every time we did a method before, in all our Comp 250 career, we would always push a method to the stack, then maybe push another one to the stack, then pop, then pop. But usually, we'd push, we pop, we push, we pop, but we don't actually make a big pile of them, right? We don't pile up our methods really high. We just, let's say we call a method, we return a method, we call a method, we return our method. So our stack never gets very tall. We never go really deep into the stack. We never go return, right? We always return one thing and then take it back. Or not always. Maybe it has a depth of 2 or something, but we never go super deep on it, right? We never make a loop which just calls methods inside of methods inside of methods. That's what recursion is. Recursion is when you push a lot of stuff onto your call stack. And that's actually where this idea of stack overflow comes from. Imagine inside of my computer, I have this RAM which stores all of these method calls, but I don't have an infinite amount. If, let's say we're in the 1980s and I only have a small amount of RAM, I might only be able to call a method like a very small countable number of times before we reach a stack overflow. So for the sake of just discussion, let's say that we can store 4 method calls in my stack, right? Or let's say it's a maximum of 3, so you can't store 4. So if I call foo for the number 3, all is well, because we have this stack, and on this stack, let's make it focus here. On this stack, we've got these 4, or these 3, and everything is fine. But as soon as I call it again, we're going to have a stack overflow. Why? Because we simply don't have enough storage on the computer, or enough RAM on the computer, to store every call. So that's how a stack overflow happens. It means you recursed too many times. It means that you pushed so much stuff onto your stack that eventually it overflowed. And the easiest way to get a Stack Overflow is to put too big of a number into this method. So imagine you have like some finite number of space and you put like 10 million as your input. Eventually, you're going to push so many stuff onto the stack that it's going to overflow. Does that make sense to everybody, how the Stack Overflow exception can happen?
Yeah.
All right, so that's the exception we need to keep wary of in terms of all of our recursive algorithms. So from now on, when we're writing all the algorithms pretty much going forward, we're going to have some level of recursion because it's a really great way to make stuff more efficient. But we have to be aware of the Stack Overflow. So we have to make sure we don't recurse too many times. Like in the movie Inception, where they don't want to, go too many levels deep into the dream. It's a very similar idea. You want to be able to do as much as you can without recursing too much, because eventually you're going to go too deep and you're not going to be able to come back because you're going to have an exception. And in fact, the Inception analogy also comes through very well. So if you know the film Inception, this part might be useful to you. If not, you can skip forward and it'll make sense to you anyways. But in the movie Inception, you know how they enter a dream, and then inside the dream they enter another dream. So they just keep entering deeper levels of dreaming. And then eventually, inside the deepest level of dreaming, which we'll consider our base case, they see, are we able to access like the memories of this dude? And once they access the dude's memories, well, they have their return. So imagine the movie Inception as a recursive algorithm. You have, let's say, a method, public void, plot, or whatever you want to call it, public void DiCaprio, whatever you want to call your main method, right? And that method is going to enter a dream. And it's going to keep entering a dream and taking with it, let's say, the cast, so like the 5 main characters or whatever. And every time you go deeper into the dream, the 5 main characters move around and they learn about the world. And you go deeper and deeper into the dream. And every recursion, well, they check. They say, can we modify the guy's memories at this depth? So are these guys' memories accessible? If not, the characters are going to do their actions. So the character's going to move around the world, shoot some people, do some action. And eventually, once they do enough recursion, once they enter a deep enough level of dreaming, eventually the condition will be true. And they can modify the guy's memories, and there they return. And if you remember in the movie, they play that big bwah sound, and that gets them out of the dream. Imagine that's like the return statement. Then they've done what they wanted to do. They modified the guy's memories. So they return from the deepest dream, then to the next one, then to the next one, next to the next one, until they wake up in real life. It's exactly like a recursion in programming. So if you've seen the movie, that would really help you visualize the whole concept of what we're doing here. Again, very quickly. So the goal of the method is to modify this guy's mind, right? So they go deeper and deeper into the guy's dreams, and they keep checking every time they go deeper. Can we modify his dreams? Then, if they can't, they will do some actions. They'll like shoot some people, do whatever, and then go deeper and deeper and deeper. Then once they get to the safe and they can modify the guy's dreams, they say, okay, great, we've modified his dreams. Now we're gonna play the bois, and we're gonna pop back up our call stack. We're gonna take all those recursive calls off our stack, and we're gonna pop back into real life. And now we're back from our recursion or from our inception. But just like in the movie, if you go too deep on your recursion, you're going to hit a Stack Overflow. Or in that movie, for instance, you can think of the Stack Overflow as, well, he goes too deep and then he goes into that horrible infinite time space. If you know the movie, you know the movie, right? If he goes too deep, it's bad. Same thing with recursion. And yeah, that's I imagine that when the people were making the film, they were thinking about recursion, because there's no way it would be that close of an analogy otherwise. It's pretty much identical. And yeah. So that's the analogy I like to think about when I write recursive algorithms, or when I just try to understand recursion. One little last note for recursion, I'm going to talk about depth sometimes. So depth means it's how many times we've recursed. So if we recurse 5 times, our call stack has a size of 5, and we are at depth 5. Depth is very useful if you want to limit your recursion. So if you have some algorithm that could potentially recurse for a super long time, but you want to cap it so that it doesn't Stack Overflow, you can track your depth and then say, if our depth is too big, just get out of there. And that's another little detail that we have. So next topic is interfaces, but before we move on to that, let's actually write a recursive algorithm. And this is going to be the recursive algorithm we saw in the first slide. So once we write this algorithm, we're going to understand what this tree, fib 54321, we're going to understand what the heck that means once we write this algorithm. All right, let's get into it. Oop, that's the wrong one, that's the right one. All right, right now we're at the Fibonacci part of our thing. So let's get to it. We don't need to have any of the other .java files right now, so we can just create a new project. Later on, we will need some other .java files, but not right now. So right now we're good. I'm just going to create a new one. I'm going to call it, I don't know, demo or something. It doesn't matter what the class is called. This is just kind of to show you guys a simple recursive method. We're going to write a simple main method, public static void main string args. And we're going to write our method. Our method is going to be called, let's say, public static int fib int input. So what is fib? Well, we're going to calculate what are called the Fibonacci numbers. So in essence, the Fibonacci numbers, if you're familiar, are like the Fibonacci spiral we've all seen before. And they are equal to the previous two Fibonacci numbers summed. So a given Fibonacci number is equal to the previous Fibonacci number plus the one before the previous. Or in more mathematical sense, we could say fib underscore, let's say fib underscore n is equal to fib underscore n minus 1 plus fib underscore n minus 2. And here I'm just saying underscore as like a subscript. So fib n is fib n minus 1 plus fib n minus 2. Is everybody kind of clear on what is a Fibonacci number and how generally we might go about calculating one? All right, so I assume it is. If not, you're welcome to ask in the chat. But the point is, these numbers are defined like that. So how do we stop this? How do we know when we've reached the last Fibonacci number? Well, I would say that Fibonacci numbers are, they're positive, right? So if the number is going to be too small, so if n is greater than or equal to 1, or if n is smaller than 1, or I guess I called it input here. So if our input is smaller than 1, this is our base case. So base case, fib of 1 or 0 or whatever are the inputs, right? Because we just add the 0 with Fibonacci number, it's going to be just the input. And otherwise, else, we're going to say return fib of input minus 1 plus fib of input minus 2. Input minus 2. So now, this might look like a bit of a straightforward method, right? We can see that here we call this method, but here I have two recursive calls. So it might look a little bit iffy. So how would our call stack look from this method, do you guys think? We don't have just one recursive call, like in my example, but we have two which are next to each other. So if I look at my slideshow, you can see that in my method here, I just return one thing. I return foo of input minus 1. So we all very clearly see that our call stack is going to look like a literal stack, right? It's going to just be foo of, let's say, n, foo of n minus 1, foo of n minus 2. You get the point. You just push them onto the stack as it goes. But can anybody tell me how they think that the call stack might look for a method like this, where we have this style, where we return it with the plus sign? Right? How could this possibly look? It's kind of abstract. It's hard to visualize, but once you get it, it'll make a lot of sense. So how would you visualize the call stack here?
Pyramid, 2 to the n numbers per layers.
Sorry, could you repeat?
Like you start with the first call, and then that first call splits into 2, and each of the 2 splits into 2. A pyramid where each layers has 2 to the n calls.
Yeah, okay. So it's kind of like a pyramid, yeah. Or in computer science, we like to call these trees. So, yeah. It's I know we haven't seen trees before in Comp 250. If you're in ECSC 202, you might have seen them. But this is not the kind of tree you might be used to. This is more like a call tree. Yes, we're still working with a stack. But if you see up here, fib 54321, that is actually the way that our Fibonacci algorithm looks. So on the left there, could you guys tell me, can you identify what are the base cases here and what are the recursive cases? On that little tree that we have up in the left side.
Base case 1 and 2, the rest is not.
Yeah, okay, so the base cases are 1 and 2, and the rest are not. If we want to use some fancy computer science terminology, we can say that the leaves of the tree, so that's the nodes of the tree which don't have anything connected to them, are the base cases. So we know that we can just return, right? Well, yeah, we can return from 2 and 1, because those are the ones where we know that our recursion is basically just finished, right? But we don't return directly from 3. From 3, we go to 2 and 1. Why do we go to 2 and 1 from 3? Well, we can see that we go to 2 and 1 from 3, because if we look at our code, if it's going to be 1, well, it's just going to recurse down 1, but then it's going to recurse, like, immediately go back up. So this one is actually just it's just going to be basically a base case. But if we have something like 3, we're going to go it on 2 and on 1. So it's still going to recurse down deeper. And that's why those are the base cases and those are the recursive ones. So before I keep nonsensing on you guys, I'm going to try calling this method. So system.println, let's say fib of 9. Now if we run this class here, oh, we got a Stack Overflow exception. So why is that? It's because I forgot to return inside of the if statement. So this is what a Stack Overflow looks like. It might seem hard to debug because you can see here, we just keep infinitely having the same method in our return. Why is that? Well, let's debug it. Before I fix it, I'm going to show you a quick trick of the debugger in IntelliJ, and Eclipse has it as well, but it's a bit harder to see, of how we can debug a recursive method. So here, I'm in the debugger, and on the left here, there's got a tab called frames. You all see that? That's where my mouse is. As I go deeper and deeper into my recursion, you can see that this is actually our call stack, and you can see how it's piling up, right? We've got all this call stack, and gradually the input is decreasing. So we go 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. But once it reaches 0, what happens? Well, it just keeps going down. So we're not actually breaking out of our recursion. We're doing nothing where we should be breaking our recursion. So you see how the Stack Overflow is happening? We just keep pushing methods to the stack. If we want to view our call stack, it's visible here in the debugger under frames. So it's quite literally a call stack. Once we start returning, these things are going to leave our call stack. And we can see that we have a depth right now of 24. So that's the depth I'm talking about. And that depth is just going to go approach infinity as we run. Blah, 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 blah. Just going to keep going forever, right? And eventually it's going to get so big that our stack is going to overflow and we're going to run out of memory on our computer. We're not going to be able to call this anymore. So what do I have to do to fix this? Well, I have to actually say return input when we reach the base case. Now that we've done that, I can rerun the method, and we get our output, which is 34, which I'm going to assume is probably correct for 9, but I'm no mathematician. But let's just suppose it's good because it's a relatively simple algorithm. Now, if I run it with the debugger, I can show you guys a bit of how this works, and maybe we can understand the tree that I showed you before. So again, we have this kind of shape where we go down in these recursions in the shape of a tree, and we recurse the way up, and it just looks kind of funky. But I think it'll be kind of clear once we see it in action on the debugger. So first, we check if it's the base case, not the base case, right? And then we keep going deeper and deeper and deeper and deeper. I think we're going to get to level 9 before we go back up, are we? Okay, so now we're at our base case. So we can see we're at a depth of 9, right? And so far, this looks like our normal stack. Everything is fine. Now, we're about to pop from our stack. So let's watch that happen. We go next, and we just pop from our stack. You can see the 9 turned into an 8. There's one fewer methods here. And now we can see the evaluation of this. Now that it's popped from this, though, what's gonna happen next? Can somebody predict what the next event is going to be? Is it gonna pop from the stack, or is it gonna push to the stack? It's going to pop from the stack. Well, it just did pop. So is it going to pop again and break us out of our recursion, or is it going to do something else? Now, let's think about our method call, right? We just finished this, right? We just finished this part. So now we're going to move on to this part. So this is actually going to push to the stack. So we're at depth 8 now, but I go next, and it's actually going to get back to depth 9, right? The reason it did that is because here we had this other recursive call for on input -2. So instead of popping where we expected it to pop, in our previous method, the one I showed in the slides, it would pop. But here, since this is like a kind of a double recursion, instead of popping, it pushes again. And now we have 9 things on our stack. Our depth is back to 9. So could somebody tell me what is going on, why is this happening, and how do we ever break out of this recursion?
When you reach the base case in one of the leaves, doesn't it like retrace back for its whole branch?
Yeah, you could say so, and that's correct. To put it in a slightly different way, we could also say that we're doing like a walk around our tree, right? Because once, see, we were at fib of, was it fib of 2, right? And that was a base case. But then we go back to fib of 3, and what does it do? Well, the fib of 3 takes us over to fib of 1, right? Because fib of 1 is the next one over. So we're kind of going from left, center, right, and then left, center, right again. Do we see that? Like, imagine we start at fib 5, then we go 4, 3, 2, right? And then we go up to 3 because we return. But then as soon as we're at 3, we say, oh, but we haven't actually figured out what fib of 1 is. So we go down to 1. Does everybody see that algorithm? It's left, center, right. We go as far left as we can. We go to the center, and then we go right. Then we go again center. Is everything evaluated? We go up. Then we go right, left, center, right, left, center, right. That is our algorithm. It's actually the same algorithm. If you were in ECSE 202, you might remember a binary tree traversal. It's the very same algorithm. If you were not in ECSE 202, don't worry. We will cover binary trees in an upcoming tutorial and in upcoming lectures if it wasn't covered already. But this is actually the same algorithm as a tree traversal. And that's really big because it helps us conceptualize how a lot of these recursions can work. Recursions are not necessarily just linear. Although they work with a stack, you can have recursions that are shaped like all kinds of different structures. And the Fibonacci one is a beautiful example because it's shaped exactly like a binary tree. And our call stack behaves exactly like a binary tree traversal. We go left, center, right, left, center, right, left, center, right, until eventually we get to fib of 5 where we go right and left. It's just exactly a binary tree traversal. That's why our stack is going to look weird. Are there any questions about it? I know that was probably a lot of information I threw at you there, and you might not have heard some of those terms, and that's okay. If you have any questions about any of those, conceptually or otherwise, please let me know, and I'll be able to answer. And if you're watching the recording and you have some questions, then by all means, Piazza and Office Hours and the future tutorials are available to you, and I'd be happy to answer. But are there any current live questions?
Yeah, just a quick question. Why
Sure.
does it go 10 times deep? Like originally? Isn't it 5 times?
Right
Or
now,
it's 2, every 5 has 2 basically?
yeah, sorry, that's actually just a point of confusion of how I wrote it. Here, my input was 9, but in the slides, my input was 5. So let me just
okay,
show
okay.
you with
Sorry, I
5.
thought we were going with 5. Okay.
Yeah, sorry, that's actually probably would have been smart of me to put the same input for the slides and the code, and I'm just going to do that right now so that we can see it in the debugger as well. And if you want to do this in the debugger as well, of course, you do it as always with the debugger. You just enter the debugging mode, and on the side, automatically, you'll have your depth. So now I'm going to go boom, 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 and you can see the highest depth I reach is 5. Then after the 5, I'm going to pop out of the 5, but I'm going to go back into it to get to the other leaf, right? So I'm going to go out of my depth 5, then back to the 1. If we look at the slides, I'm going 5, 4, 3, 2, 3, 1, right? Now I'm going to keep going through. I'm going to pop that 5. Now I'm going to go 4.
Did you show the screen for you?
Oh, yeah, sorry. Had the slide show up there for a second longer. So I'll just show it quickly again. We go 5, 4, 5, and we kind of go left, center, right, left, center, right. If only I could put these side by side. Maybe I can. Give me a second. Image slideshow. Let's turn that on and just put it right here. Okay, so I'm going to put that right there, and I'm going to put my screen share. Where's my screen share? Gosh darn it. Screen share over here. So now we could hopefully see both at the same time, maybe. Ooh, I'll have to shrink my screen share, or I can just shrink my IntelliJ window here. Let me do that. So I just want to show you guys side by side what's going on. No, I don't want to edit my screen size. I want to edit my, I want to edit my IntelliJ size. So let's do that. Boom, boom, and to the side, and get rid of that. Okay, sorry about the delay there. So what I'm doing is I'm going to show you guys live how this call stack corresponds to the tree. So here I'm going to go next, and it's going to go deeper and deeper into the recursion, right? 2, 3, 4, 5. So right now on the tree, we're at the very leftmost corner. We're at fib of 2 on the very left. Do you guys see that?
Yeah.
Okay, so now we're going to go next, and we're going to go pop up from there, and we're going to get to fib of 4. So now we're at this fib of 3 that's 1 up from the left, right? Next, we're going to go down to fib of 1. So we're going to go next, and we're down to fib of 1. And then we're going to go back up to fib of 3. But now, since we're back up to fib of 3, we're ready to return. So we can just return from that, and now we're up 1 level higher. But now we're at fib of 4. So fib of 4 is going to send us back down to fib of 2, which is going to send us back up to fib of 4. And now we're currently at the top, I believe, or we're almost at the top, right? We're just going to climb up our tree, and now we're going back down into fib of 3, and we're kind of climbing the right side of our tree. And we're going to go through the entire right side of our tree to the maximum depth here, which is 4. And then we're going to go back up our tree, just like on the other side. Bam, 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 until we get right back to the start, where our input comes out. Bam, 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 as... Oh, come on, still recursing. Come on, get out of there. And our input comes out right away afterwards as 5. Alright, so here was our traversal. So that's kind of how the algorithm looks. That's how it works for us. And that's generally how a Fibonacci recursion looks. You don't have to memorize all the different patterns of how the recursion looks for all the different algorithms you're going to write. But the Fibonacci one is a nice one to think about because it's kind of a good example of what they can be like.
Excuse me, I have a question.
Sure, what's up?
If 2 is one of the base cases, shouldn't we check also for it in the input, or is the base cases 1 and 0?
The 2 is essentially a base case, but in this code, I just saved a few lines because let's think about what happens with 2, right? If the input is 2, we're going to say that the input is going to be, it's going to be input of 1 plus input of 0. So it's just going to go to input of 1, and it's going to do like a 1 depth recursion. So it's not really going to do much. So although it is technically in this code not really a base case because it still calls it on fib of 0 here, well, fib of 0 does nothing, right? Fib of 0 is useless. So essentially it just calls it once and it doesn't do the tree style recursion. And in some other implementations of this, you could also say if, input equals to whatever, right? I just saved that line because essentially it does the same thing like this. But you are right. It's technically
makes
not a
sense.
base case.
Makes sense. Thank you.
For sure, yeah, and thank you for pointing that out because it is technically.
One last thing: is this getting the sum of all the numbers of the first 5 terms? Is that the point of this particular method, or am I understanding it wrong?
This method returns the nth Fibonacci number. So if you know, from math, I don't know if you've seen it somewhere, maybe in Math 240. I don't know if it's shown in Math 240, but in some sort of math class, you must have seen Fibonacci numbers. The math teacher probably went on about how they're everywhere in real life or whatnot. Like everything is based on Fibonacci numbers. The mathematicians like them. But the point of the Fibonacci numbers is that each Fibonacci number, the nth Fibonacci number, is defined as the sum of the previous Fibonacci number and the Fibonacci number before that. So if we look at the sequence, we can just put them out, and then we can see that this is just a method to generate them. So we can say for int I equals 0, I is less than, let's say, 100, well, maybe 10, I plus plus, and we can do the fib of I, and this will show us the first 10 Fibonacci numbers. We'll do bam, bam. All right, now if we run that, we can see that it goes like 1, 1, 2, 3, 5, 8, 13, 21, 24. So those should be kind of familiar to some of you. If it's not familiar, it's okay. The math of it is not part of Comp 250. It was just an example of a recursive method. The point is the Fibonacci numbers are like this sequence, and they can, of course, go on to infinity.
Thank you.
All right. So if there's any more questions about these concepts of recursion and, Fibonacci number algorithm or any of these, now is your time to ask. And if not, I can move on to interfaces, which is the other topic for today. So let me know if there's any questions regarding anything recursive, anything related to these algorithms, any questions about the concepts. All of them are welcome. All right. Oh, will we have assignment 2 question time? Yeah, you're welcome to ask assignment 2 questions at the end of the session, and I will also be running a dedicated assignment 2 recap, or at least I'll try to, in the coming days, maybe tomorrow, maybe a different day. I'll keep that posted on my courses, and I'll try my best to run an assignment 2 review session before it's due. But yes, assignment 2 questions are welcome today as well at the end of the session. So yeah, assuming there's no recursion questions anymore, I'm going to move on to interfaces, which are our other topic for today. Right now we're going to be at the what is an interface question. And the what is an interface question can be answered pretty simply. An interface is like an abstract class, but way more abstract. So you know that class versus abstract class states that a class must have everything instantiated. So every method in the class must be able to run. However, you can also create an abstract class, which is a class where not everything can run. So you can have an abstract method which you don't fill in. You just say this is a method which has to be there. in the class that we are extending, right? That's the difference of abstract class versus class. Well, interface versus class is a similar question. An abstract class or a class are able to have things declared, right? So for every class may have some sort of methods declared. However, an interface may never have any methods declared. So if you imagine that there's like a line. We have, on this side we have class, where everything is declared. Right? In a class, everything must be concrete. You may not have any abstract methods. Everything has a body. Everything is implemented. Right? Then in the middle, we have abstract classes. Abstract classes can be kind of half not done and half done. So therefore, when you have kind of archetype. So every dog is an animal. The dog would be like an abstract class because a lot of it is already filled in, but some of it is missing. Right? It's just kind of a template with a few things missing. Now, on the very opposite side of that, here, we've got interfaces. Interfaces have absolutely nothing filled in. They are just a list of methods which we have to have. They tell you nothing about how they're implemented. You're not allowed to have fields. You're not allowed to have anything. All you're allowed to have is a list of methods. In some modern versions of Java, you can actually implement stuff, but we're not covering that because that's not Comp 250. That's way beyond the scope. For the sake of Comp 250, an interface is like a class, but nothing can be declared. Imagine an abstract class where everything has to be abstract. So again, a class, everything has to be filled in. You're not allowed to have anything abstract. Nothing is missing. Everything is there, right? An interface, everything has to not be there. You can just have a list of method declarations and no bodies. Then in the middle, we have an abstract class. An abstract class can have some abstract methods which have no bodies and some methods which do have bodies. Does that kind of make sense? All right, so interfaces have one more superpower that's super useful to us. An interface can be extended multiple times, but when I say extend, what I really mean is implement. In Java, we call it extend if you're extending a class, and we call it implement if you're implementing an interface. Why do we call it implementing? Because you can do it with multiple. So you know how every class you can only extend one thing. You can say dog extends animal, but you cannot say dog extends animal and furry, right? You can only say dog extends animal because you can't extend multiple classes. Interfaces are more powerful because you can actually implement multiple. So you could say, for example, stack implements, like say, iterable and comparable, or whatever other interfaces you want. All the interfaces usually have able as the suffix, so you know it's like a naming convention. Every interface is something able because interfaces kind of represent a capability. Interfaces represent that something has the ability to do something. Another example would be if we have a simulated economy and we say that everything that can accept or give money has, let's say everything can accept money will have a payable interface. So we can say that every single entity which you can pay is payable. So a person might be payable, but also a restaurant might be payable, and a bank might be payable. See, these are all completely unrelated objects. They have nothing to do with each other, but they all share the functionality that you're able to pay them, right? Just as you can pay a person, you can also pay a bank, or you can pay a restaurant. And these things are completely different. A person and a restaurant have essentially nothing in common, right? So they're not extending the same class. Rather, they share a functionality, so they both implement the same interface. The reason that we can have multiple interfaces is because they just represent a functionality. So a bank might be payable, and it also might be able to give you a loan. And although a person might have the same functionality, let's just say a person can't give you a loan. So a person can pay, but maybe a person can't give you a loan. So for that reason, a person in a bank can have different sets of functionalities, but since these functionalities have nothing to do with the nature of the person or the nature of the bank, they are not exclusive. You can have multiple of them. Does that make sense? Why, design-wise, we would use an interface? All right, well, to get acquainted with the concept of interfaces, I'm going to transition us over back to our screen, and I'm going to create a new interface. And we're going to create a couple of classes and implement it just as I explained there. So I'm going to create a class bank. Let's just say new Java class bank. Well, before I create that, actually, let's create payable. So payable. Payable is an interface. And in an interface, it's just like a class, but you declare public interface and the name. And usually, the naming convention states that an interface is something-able, right? That's just the way we name them. And let's just say that a payable can accept money. So we'll say public void accept money int amount, right? That's all we care about. Anything payable can accept money. So now let's say that we can pay various things. Let's say we can pay a person. So we'll say person. And a person might have, let's say a wallet. So private int wallet. And if we want to add the functionality of a payable, what we can say is here at the top we can type implements payable. And now we're going to have a compile time error because an interface, just like an abstract class, states that every method in the interface must be instantiated. So how could we fix this compile time error? Understanding that payable has this method here. Let's just open it there. So payable has a method accept money. And person wants to be a payable. So what does person have to do?
Has to implement accept money.
Exactly. So we have to have the same method here. So we can say, we can either make IntelliJ do it for us, but since we're teaching now, I won't do that. I'll just say public void accept money int amount. And now the class will compile. But since I wanted to do something, I can say maybe wallet equals 0. We can say wallet plus equals amount, right? So now we can accept money as a person. Now, let's say we also want to be able to pay money to our snake from the snake game. You know, who says snakes should be unpaid? Maybe snakes also deserve a salary. So we can also implement payable in snake. Payable. And that's outside of the package, isn't it? So I'll have to say, I'll just move it in. No problem. Refactor. Okay, so now the snake can be a payable. That's just a packaging issue. Snake. All right, but now you can see that we don't have the method implemented. So to be able to do it, I'm going to have to implement methods again. Now I'm going to let IntelliJ do it for me. And here we can see that the snake needs to also be able to accept money. Well, since the snake doesn't really care about money, maybe instead of accepting money, we can give the snake more points for its game. So maybe we could say, snake dot... What can we do? Can we add some cells to it? Well, we want to give it some more points for the game, but we don't necessarily have the ability to do that, so I'm just going to say snake dot add a new cell, because you know the snake wants to grow, so we're going to add new cell, and it's going to be completely off the grid. Let's say negative. This is just snake game stuff. Don't worry about it. The point is, we just gave the snake some food because it will accept, well, that amount of money worth of food. And let's just say we don't care about the amount. It's just when you pay the snake is just going to buy some food. So when the snake does this, it'll do a completely different functionality than the person. But both of them are able to get paid, right? So you see how this works? These two completely unrelated classes can both get paid. And if I make something like a bank as well, and also implement payable, the bank can also do its own thing. So it can accept money, but let's say that instead of just taking the money, the bank wants to have stocks. So you could say maybe the bank has a method, private void by GameStop, right? And then int amount, and maybe not void. Let's just say this will represent the number of GameStop stocks they own. And now we'll say private int GameStocks equals 0. And we'll say that they just buy GameStop stocks. So they'll say GameStocks plus equals amount. And here they can say buy GameStop amount, right? So this is various ways of things getting paid. So you can see that every various kind of object that implements payable is able to get paid. But every single one of them does something different with the money. And for that reason, these various classes all implement payable, but they all handle it differently. Does it make sense here how interfaces kind of work and the paradigm we're working with, how it works, how we do it?
It's very similar to the abstract class, just it's not like confined by just being a part of the abstract class. It could be just any class.
That's
Just have
right.
to implement.
Yeah, exactly. It's like an abstract class, but it has no restrictions. It's not bound to being any particular object, right? A bank is not bound to being an instance of something else. The bank, all it's saying is the bank is able to get paid. You don't care what the bank is or how it's made. You just care that the bank can accept money. That's what interfaces are. You're exactly on the spot. It is just like that.
This is what the quiz is on this week, right? It's on this part of the lectures. Like
I'm not
interfaces?
sure, but I can check really quick. Sorry, I haven't. I've just been on reading week, so I haven't been up to date with what the quizzes are about right now. But I can check very quickly, and I can get back to you. And maybe if there's an example quiz, I can go through an example quiz question on it as well. Let's see, quizzes. Quiz for practice. Let's just look at it. Okay, so our quiz for practice is, it is about interfaces as well, and about iterable, and about generics. So generics we covered in a previous tutorial, and interfaces are exactly what I'm doing now. So in this quiz that we have coming up, in the example quiz, we have questions about iterable and comparable. So could somebody tell me what is iterable and what is comparable?
Interfaces?
Yeah, do you know what they do?
Is it a way for us to define, like, if you want to parse through a set of objects of a class, like, in what way you want to do it for iterable, and in what way you want to, like, rank things based on whatever characteristic you defined for comparable?
Sure. That is a good explanation of it, yeah. And what we can do is I can show you what it does by implementing it. Here, I've got a linked list from a previous tutorial. If you want the Java file, I'm just going to send that over to everyone now, so we can follow along. Open that in Explorer. We want list of links, we want stack and queue, and I'll take the benchmark too. So here, these are the ones we're working with. I'll just send those to the Zoom chat, and of course they're going to be on GitHub for the people watching on the recording. So these Java classes define our linked list from before. Now, I am going to propose to you guys a question. What if I want to iterate through my linked list? So what if I want to say for string s in L, right? Well, is L a linked list? Yeah, it is. So for string s in L, how do I make this work? I want to do a for loop like that. What do I have to do?
First, it has to implement iterable for this for loop to work.
Yes. So this for loop actually calls iterable. This is just a fancy disguise for iterable. So how do we implement iterable? Well, it's an interface. So we do it the same way as we did with payable. We say implements iterable. But when we do that, we're going to have an interesting conundrum. I'll also say E for this. Now, with iterable, it's generic. And remember generics, if you remember them from the previous tutorial, they mean that we don't define what type goes here. It means that we just have some sort of generic type in here. And here it's E. So it is going to be able to iterable, and it's going to iterate over E's. Does that make sense to everybody? Since the list of links contains objects of class E, the iterable will also contain objects of class E. So that explains the triangle brackets. So when I implement methods on iterable, it's going to implement these various methods. I'm going to press OK on it, and it's going to implement the one method we need, which is public iterator E iterator. But now we have a problem. How do we get an iterator? And what is an iterator?
Isn't that what you're doing? You're defining the method?
Not quite, because I just defined an iterable, right? Iterable is not the same as iterator. And that is the biggest trick of these things. This is what you're going to get nailed on the quiz, and this is what's going to be hard on the assignments. It's the fact that iterator and iterable are not the same thing. An iterator is a little separate object, which kind of leeches onto your data structure, and the iterator is what handles going through your data structure. Why do we have that? Well, imagine you want to go through your list of links in two different places. You don't want the list to be responsible for iterating through itself, because if the list is responsible for that, that means you can only really do it one at a time, right? If the list tracks your position in the list, then how are you going to iterate through it again a second time if the position has already been tracked once? This will make more sense when I implement it, but the point is we need a separate object which iterates over our list. And there's two ways we can go about doing this. The first way that I'm going to show you is not at all how we see it in class. It's my own way, and I think it's more clean, but this is not how you're necessarily going to do it in the assignments, and what it's called is an anonymous class. Can somebody tell me what is an anonymous class? Anonymous classes are this little detail You might see it on your quizzes, and you might see it on just in some trick, but you're probably not going to see it in your assignment unless you want to. To do an anonymous class, you do something illegal. You create a new instance of something which cannot be instantiated. So normally, right, creating a new iterator would give me a compile time error. You see that? So if I just say return new iterator, why is it not compiling?
You haven't. It's an interface, so you can't. Or is it because you haven't defined it yet?
It's because you can't
Instantiate.
instantiate an interface. That's right. Again, as we previously said, because an interface is just a list of methods, and we don't know what these methods are going to be, you can't implement an interface. Or you can't instantiate an interface. You can implement it, you can't instantiate it. So what we need to do is we need to define it somehow. But instead of actually writing a new class, I can put little curly brackets here. And when I put the curly brackets, I can also say implement methods. And now I have what's called an anonymous class. Why is it anonymous? Because I never actually declare this class. This class only exists within the scope of this method. It's something that implements iterator, but I never named it. I just implemented the methods. This is a trick that can save you a lot of lines of code and can make your code a lot simpler. But it's not what you're going to do in assignments. Now the point of an iterator is just that we have to fill in this method. Right? We just have to fill in, or we have to fill in these methods. So for has next, we can say, let's say, for example, we're going through our current thing. So we can have a node current or a node e current. When we start our iterator, so let's say we say public iterator. Well, we can't do this because it's an abstract class. But let's try it, right? Or it's an anonymous class. So since we can't do that, we're going to move it to a actual class. So this is the anonymous class. We can have fields in it, but the constructor call is dubious because here we don't put anything through our constructor. So we can't very easily put a constructor in an anonymous class. We could do it, but it's not clean. So what I'm going to do instead is I'm actually going to create an inner class. Just like I have the class node, I'm going to have a class. I'm going to call it maybe list of links iterator. And this class is going to contain our iterator and is going to implement iterator. And this is how we do it in assignments. So inside of our class, we have an iterator class. And instead of returning this with the curly brackets, we can say return new list of links iterator. And since list of links iterator implements iterator, it works. So beside the anonymous class declaration, we can also do a regular class declaration. And now in here, I can do it the way I want. I can have a field, let's say private node e cur, and we can have a constructor. So we can say public list of links iterator. And in the constructor, we're going to say cur is equal to head, let's say. And now what we can do is we can say if has next, let's just say return cur dot next is null, or is not null. And next we're going to say e out is going to be equal to cur dot get, or cur dot payload. We're going to say cur is equal to cur dot next, and return out. So does this make sense to everybody? This very simple class. Has next checks if there's something else in the list. So this checks if there is something left, or if we're at the end. We're at the end. Can we keep iterating? And this one iterates forward and returns whatever. So this one iterates forward and returns whatever. And this way, we have the ability to loop through. Can somebody tell me how we can use these two methods to loop through our data structure?
If has next, then next.
Yeah, you could do if, or you could do while has next.
Yeah, while has next and current and then next.
Exactly. And in fact, that thing you just described is exactly what this for loop does. In fact, this is exactly identical to saying while L dot has next, well, I guess L dot iterator dot has next your string s is equal to l dot iterator dot next. And that's it. This is exactly equivalent, right? This and this are the same thing. They're the exact same. Now, here Philmon asks, can you go over what the purpose of anonymous class is? Yes, the purpose of anonymous class is, see here, I've declared a third class, right? I've created list of links iterator. I don't have to do that. Instead, what I could do is instead of saying new list of links iterator, I could say return new iterator, and then implement it here. Why do I do that? Well, it saves me a class. So I don't have to declare a class in my file. I can have one fewer classes, and that makes my code cleaner because, well, I have less stuff declared, right? I never have to create this class outside of the context of here. Since I only create the class once, I don't actually need to have all these lines here. I don't have to have this line. You know, I might not have to have the constructor. All I need to have is the iterator right here, right? I only ever call it once. I only ever call the constructor once. And because of that, it might be more efficient for me to never actually declare the class, but to just put it in the curly brackets and declare it anonymously. It's not strictly necessary for anything. You can go without doing it. It can just save you the class declaration, and it can make your code a bit cleaner because when somebody's reading it, they're going to see here we've got like, what, 2 classes inside of list of links? That seems like a lot. Does that make sense?
Hey, excuse me? If I remember right from the lecture, I think Professor said that for has next, the way it was implemented is cur checking return cur not equal to null, because in the next method you're getting the payload and then you're moving on to the next afterwards, if you understand what I mean.
Yeah, we can see maybe this one will cause an exception, and we can see if it will when we run it. So yeah, let's see if it works. We'll go into here, into my main method, and we've got this enhanced for loop, and let's just say we're going to add a bunch of stuff to our list. We're going to say L is equal to new list of links, and we're going to say L dot add, let's say hello, L dot add world, and L dot add yo. Right now we're going to say print out L, so system or system.out.println s. Okay, and let's see if it worked. So we're going to go demo, we're going to run it. Or is it demo? No, it's going to be this, whatever this is. It's going to be a list of links main. So wait, run it. List of links main. Where is this? Where is this? Here, right here. Run it. So it looks like, ooh, yeah, it prints out hello yo world, which is not exactly in the right order, is it? Well, I'm just going to remove all the previous stuff, and we're going to see if it did it correctly. Oh, did I forget to say new list of links? List of links of type string. L is equal to new list of links. Okay, now let's try it, just to make completely sure that everything works. Yo world. All right. So you are right. We do actually miss an element. So because we say if cur.next is not null, we actually miss it when we hit the last element. So yes, you were right. We do need to actually say if cur is not null. Now we could actually do this differently, and that way the original way is correct. How do we do it? We do it like that. So if I put cur.next in the line order slightly differently, now this check is correct. So that's another one of the tricks of the iterator, is you have to know when cur.next is supposed to be null and when it isn't supposed to be null. So here we missed the first element. Cur.next. Here we missed the last element. Oh, yeah. Here we missed the last element, and here we missed no elements. All right. So that's the general list of links iterator setup, and that's how an iterator works. You can test if your iterator works. To test an iterator, what you have to do is you have to put in a bunch of stuff, and you're going to see if the for loop gets all of it. So the most common mistake, as was pointed out, was to doing the has next or the next wrong. And it's very easy to get these wrong because if you put a dot next where it's not supposed to be, or if you put them in the wrong order, you're not going to get through your whole list. But like this, we actually do get through our whole list. So that's the concept of the iterator and how it is implemented.
Okay, question. Why isn't it in order? Why is it printing first yo world hello and not hello world yo?
I think that's because here we've implemented it as a queue. So what it's doing is that when we call
Added.
it's going kind of backwards. What we can do is, since we also have the stack in the queue class, we can override our iterator and we can make it go in the correct order for a stack or a queue. That's since we're past the time today, and I'm sure you guys have lots of A2 questions, I won't do that right now. But if you guys want to, for your own exercise, you guys can implement iterator on stack and queue, and you can do it in the same order as it pops. And that way, you can maybe see more hands-on how the iterator works. Now, right before I go, I'm going to give you, before we get to assignment questions, I'm going to give you two things. First of all is going to be comparable. It's another interface, and it turns out to be pretty simple. Comparable lets you sort stuff. How does it let you sort stuff? It lets you compare the values of things. What are we going to be able to compare? Let's say we can compare our linked lists. Let's say I want to implement iterable and comparable. And it can also be compared to another list of links of the same type. So now if we are able to compare it to a list of links, we can implement methods. And now we can say, for example, return o.size minus this.size. So what does this do? Well, let's say when we compare a list to sort them, if we want to sort lists, we can sort lists by how long they are. So when I have this method, when we compare lists, it's going to return the difference between their sizes. And the int this returns kind of their priority or their score. So let's say we have a list of size 10 and a list of size 1. We want the list of size 1 to go before the list of size 10. When you compare a list of size 1 to a list of size 10, you get -9. Since it's a negative number, you have to swap them over, if you remember, like bubble sort. And that's what compare to does. It returns an int representing the difference between two various objects. Here is a very simple implementation of comparable, where we just compare lists by their size. Now, if I have a bunch of lists, let's go to my main method. I've got L, which is of length 3. Let's also create list of links string M, which will be a new list of links, and it'll just be empty. And then we'll have a list of links, integer, let's say. They're all different types. Or I'll do string again. String P is equal to new list of links, and this one's going to be full of a bunch of stuff, so let's just say it's going to have yo world hello again. It's going to be P, and now we have all these three of different lengths. P, 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 and P. Now if we add these all to a data structure, let's just say array list of links string list is equal to new array list. And now list.add L list.add M list.add P, and we say list.sort, and here we can say list of links, or I guess p.compare to. There. So that's our sort of our method call, right? Compare to. Is it compare to? I believe it is. Or I guess say list of links.compare to. So here, this is how we do it. So we're going to add all these in. They're going to be out of order. And then we're going to sort them, and the compare method is going to be called. So I'll just start it over here on the debugger. It's going to say we've got a new list of links, or a new array list of links. At first, the array list looks like this. It goes 807, 808, 809, and it goes size 306, right? And then when we sort it, it's going to go of size 630. So you can see how it gets into order by using the compare method. Are there any questions about comparable?
Sorry, you went a little fast. Could you just redo the debugging, please? Or?
Sure. Okay, so once again, the compare to method, what does it do? The compare to method will compare two objects by whatever you want, and it will return a number. If the number is negative, that means the one you're comparing is smaller. If it's positive, that means the one you're comparing is bigger, which helps you sort. So here, I create a new array list of lists of links, and I want to sort them by the size. So to sort them by the size, I implement my compare to method. My compare to method says we compare the size of the one we pass to the size of this one. if the size of the next one is bigger, it's going to be negative, so it's going to swap them over. And eventually we're going to get it into order from smallest to biggest. So our array list starts off like this, where it's going to be in order of 3, 0, 6. So that's out of order, right? Now, when we click sort, what's going to happen is it's going to call the compare to method, and it's going to compare the sizes, and if the output is negative, it's going to swap them. If the output is positive, it's going to keep them in the same order, and at the end of the day, it's going to go 6, 3, 0. So it's going to be in order, largest to smallest, and it's done. How did it do it? Well, the sorting algorithm was made by Java. We didn't write the sorting algorithm. We just told the sorting algorithm how to compare items. How do we know that they're out of order? How do we know which order they're supposed to be in? We do that using compare to. It's a very simple method. All it does is it returns an int representing whether they're in order if they're negative, or they're in order if they're positive, and out of order if they're negative, depending on which order you want to sort them in. Hopefully that makes sense. All right. So if there's any, what does the colon mean? It means that it's going to be the method with this name inside this class. So list of links colon compare to means the method compared to inside of list of links. If I did, for example, list of links colon new, that would be the constructor. List of links colon size would be the size method. So it's saying here it's going to say / it's going to say we are doing method called compare to inside of class list of links. That's what the notation means. Are there any further questions? I just had a question about runtime tester. It doesn't count as an import in IntelliJ, right? Just want to make sure it wouldn't get flagged since we can't import anything in our files. It does count as an import, but it doesn't matter because you shouldn't be importing it inside of your solutions. You should be importing it inside of your tester. And in your tester, you can import whatever you want. So the difference is between your assignment and your tester. Inside of your assignment, you can't use the runtime tester to create new solutions. I don't know how you would, honestly, but if somehow you're a Java wizard and you can use the tester to create a solution, we don't want that, right? So you can't import it into your code. But what you can do is you can import it into a tester and use it. And we don't care what you import into your testers because we don't check your testers. So again, runtime tester can be imported into your tester, but it can't be imported into your assignment. Hopefully that makes sense. There's not really any need to import it into your assignment. All right. If there's any more questions, I'm happy to answer them now. And otherwise, I'm going to give you guys a teaser of what we're going to do on Friday, which is going to be a lot more advanced, but it's also going to be really, really cool. So we're already in the snake class, so I'm going to do a quick git pull. And I'm going to go into the recursive AI branch. Fancy. And if I run with the recursive AI, it's actually going to play snake for us. So this is what we're going to do on Friday. On Friday, we're going to learn about how recursion can be applied to running a game. In fact, to solving a game. So if I check off use AI, we can see that it's actually going to calculate all the scores from where it's potentially going to go, and it's going to use that to play the game for us. So using recursion, we're going to be able to create an AI that can perfectly play snake. This AI is very good at snake, and depending on the depth, it's going to always succeed. The depth is how deep we recurse, and that depth correlates to how far the snake is able to see. So if you see the gray rectangle around the snake, that represents the snake's field of view. Since it can't see any food, it's just going to kind of not kill itself. But if we increase our depth, then it's going to run much longer, because the recursion is going to go into depth 10. It's going to see everything 10 depth around it, and it's going to be able to win the game, because the snake will be able to see everything on screen. So this is what we'll be covering next time as a topic in very advanced recursion. It's going to be way harder than what you expect, but if you can understand it, you can understand pretty much any recursion. So that's something to get you sort of hyped up for next time, when that will be the focus of the day. And hopefully this is something you guys would be excited to see, because it can basically solve, this algorithm is the same one that's used to solve pretty much any game. So if you have chess, if you have tic-tac-toe, if you have anything, you can solve it using this recursive algorithm, which will look through all these possibilities and rate them. So that's going to be next time. This time, I'm ready to answer your questions relating to assignment 2 and whatever else. It says, for reconstructing the shuffle deck in array.shuffle, how can I make the following instructions in a loop? Now, I don't know if I can answer that question specifically right now. That might be better for office hours. But if I were to say for shuffle, remember that when you're inside of a loop, you're not supposed to really modify the data structure you're looping through, right? So let's say that you are looping through a data structure A. You don't want to make any modifications to A while you're looping through it, because the loop is going to be thrown off. You start the loop to go, let's say, until A dot length. So if you remove something from A, it's going to go out of bounds. Or if you add something to A, it's going to be out of bounds again. So you don't want to do that kind of modification. Now, are you able to move things around inside of the thing when you loop? Sure, you can swap elements around. So you can say like A at index I is equal to A at index I minus 1, but then you have to keep track of your indices. And remember that when you're working with a linked list rather than an array, you can always create a method. So maybe instead of using the square brackets, you could say array, or I'd say A dot swap, and then node comma node. And then that swap method you could fill in yourself. You can create a private helper method called swap, which can swap nodes. So the way I would do it is I would probably use a private helper method for swap. I'd make sure I'm not resizing my data structure at all, because remember, you can't resize or remove when you're looping. And I would try to do a private helper method for that. All right, are there any further questions?
Yeah, quick question regarding the decode method, where you're supposed to. So basically, I use like a kind of like a finding the position of each character, right? So we have a string of just letters, and I'm separating each character to find that position, but I'm getting kind of confused to how to like retrieve the original position of the original letter. I don't know if you understand the question.
Yeah, sure. One sec. Sorry, I'm gonna have to go in a second because I just had like a delivery come in. But I'll try to answer your question as quickly as I can. If I don't give a detailed enough answer, please come to office hours. But I understand your problem is that you want to keep track of the original thing while you're iterating.
No, so now this is a decode method. So we have our string, and we want to find basically the original position by shifting each letter by its the representative of in the key stream, right? We have the key stream array. So each one corresponds to one character. So we want to shift it to the original, or like I guess shift it to the left, I guess.
Okay.
So would we have to do the position of that character minus, because I'm getting like negative values, like minus the key stream.
Sorry, it's kind of hard for me to conceptualize.
It's
like
okay. It's
how
okay.
your code
I'll
is.
just go to office hours.
Yeah, how your code is behaving. But I'm running office hours tomorrow at 11:30, and you're welcome to come by, and I can take a look at your code and I can help you with that. Sorry, it's hard to conceptualize it all when it's just in English.
That's
so
okay,
I can help
fine.
you by looking
Thank you
at
so
your
much.
code in office hours. Thank you so much. All right, guys. If you have any more further questions, please come to office hours, the next tutorial, or Piazza, and I'll be happy to answer. Thank you so much for coming, and I look forward to seeing you on Friday when we're going to implement that cool thing. All right, see y'all later. Bye-bye.